So that would tell us that is a measure of the frequency. Like for a certain amount of time, how frequently are the waves hitting you? So for this, let's say this amount of time, we have 3. That's not the frequency, but I'm just telling you that let's assume that's 3. It's the frequency is, let's say, 3. That same amount of time where 3 of them hit you, when you get to the long wavelengths, you only have 1 of them hitting you. So you can see how the greater frequency has a higher energy. And the shorter the wavelength, the more the frequency, right? Because there's a long wave and only one of them is going to hit you in the same amount of time. So this is low energy, and this is the high energy. This is the short wavelength, and this is the long wavelength. So frequency and energy are directly proportional. Higher frequency, higher energy. The wavelength and the energy are inversely proportional. The short wavelength has a really high energy. That's this. And you can see how things work basically from what it is. Here we have the radio waves of, let's say, a meter. They are completely harmless. As we speak, radio waves are flowing right through us, harmlessly, and getting into your radio receiver, wherever you have it. Completely harmless. Such low energy, they don't do anything to our molecular structure. But then when you get to the ultraviolet, that starts to break apart the skin, right? You don't want to get into too much ultraviolet rays from the sun. You'll ruin your skin. It's damaging to the skin. The X-rays, they penetrate, and they're such high energy. They penetrate and they damage as they do. That's why we stay away from X-rays if we can. Gamma rays that's radioactivity. That's really dangerous stuff. Higher energy. It destroys or disrupts the electrons from atoms and molecular structure. You definitely don't want to be near those. Near that. That's deadly. So high energy, that's the idea. It's high energy. Short wavelength, high energy. The radio waves, the harmless, easygoing stuff, that's radio waves. That's easy. That's long wavelength. Okay, so we see how these things are related. Visible light is like a small portion of this electromagnetic spectrum. And the longer wavelength is red. The shorter wavelength is blue or violet. It takes up a little bit of space. To this side, the less energetic is infrared. It's not visible to us. We only see the visible colors. So infrared is of lower energy. It's important. It's still electromagnetic. It's part of the electromagnetic spectrum. It's used in forensics as well as many other branches of chemistry, or many other chemical analyses and physics analyses and so on. Higher energy is ultraviolet. Okay, that again we can't see, but it's around. So we know the sun gives it off. And again, that's very important. And past that is X-rays. It's even higher energy. But here's where visible light fits in, between the infrared and the ultraviolet. We cannot see any of those, just the visible light. Some animals can actually see infrared or ultraviolet. I think there's a mantis shrimp that can see the infrared and ultraviolet. Anyway, I did mention that the wavelength is inversely proportional to the energy or to the frequency. That is shown by this equation here. C equals lambda, which is the wavelength, and this is the Greek nu. So C equals the lambda times nu. C is the speed of light, that doesn't change, is equal to the wavelength times the frequency. So if you increase the wavelength, then the frequency has to go down. Or you increase the frequency, then the wavelength has to go down. That's how they're inversely proportional. As mentioned, light is both a wave and a particle, and we've mentioned how it works as a wave. We've shown it as a wavelength, and we've mentioned that. We're going to be using it as that. Mostly, light is just it's not not coherent, meaning it's of several different wavelengths at the same time. White light is composed of all different colors. Green light has a lot of the green wavelengths. The blue light has a lot of the blue wavelengths, but light can be coherent of only one wavelength, or pretty much. Again, it's never perfectly one wavelength, but as close as we can get is what comes out of a laser. That is called coherent. It is only one wavelength. It's composed of only one wavelength. When light, not necessarily from a laser, although lasers are very often used for this, when light is put onto matter, what can happen is light can get reflected. That's when we see it. Some of it always does get reflected. Some of it gets absorbed, meaning the light energy is absorbed into the molecules that light hits, or it can be scattered, depending on what the material is and how much of it gets reflected, absorbed, and scattered, and which parts of it get reflected, absorbed, and scattered. So we can analyze what gets absorbed, let's say we shine light on it, and we see what bounces back to us, what gets reflected to us. Well, the others must have been absorbed, let's say. So we can tell by what got absorbed and what gets reflected by what the material is, at least in theory. This is what they call spectroscopy, because of, as we mentioned, the electromagnetic spectrum is sort of coming from that, spectroscopy. Shining light on something, checking the light that gets absorbed or reflected, and finding out what it is based on that. So that sounds just like what they do in Star Trek, when they send their beam out to the planet and they come back, oh yeah, this is an Earth-like nitrogen and oxygen atmosphere. Yeah, that's what they do there. It's not as easy in real life as they do in Star Trek, but that's the basic principle. Shine light on something, see what gets absorbed and what gets bounced back, and you can tell what the material is. Different materials absorb differently, different materials reflect differently, and scatter differently. So, now for the glass. In criminalistics and forensics, glass is very often found. Remember, criminal activity can be violent, and when you have violence around glass, well, it can break. So you very often find glass at crime scenes in the shattered form, usually. I mean, you find it in not shattered form, but that's usually unimportant, unless you find fingerprints on it. But anyway, you can find glass all over crime scenes very often. Glass is all over the place. We all like the glass. We all like to, for whatever reason, we like to look through things, and that means windows and car windows and windshields and all kinds of stuff. Even bottles, or we like to see inside bottles, so we make them of glass. So we find glass all over the place. It is very often found at crime scenes. Also, when it's shattered and little fragments are left, are shattered again. Little fragments are found all over. They scatter all over the place. They can land on perpetrators without them even knowing. And glass doesn't decay. So if you catch the perpetrator, months later, or you see his clothing, the clothing that was worn, by the months later, the glass that was there at the crime scene is still there. So let's talk about different types of glass. There's many types of glass, but we're talking about some of the main kinds. Glass is made of silicon dioxide. Remember, this is the molecule. Effectively, it's sand. Sand can be silicon dioxide. You melt that, you'll make a glass. You'll make what they call quartz glass. However, quartz glass can, it's hard to melt and then fuse with something else. It gets tacky when you heat it up too much. So it's important in various fields of chemistry, especially spectroscopy, that glass be specifically only made of quartz. But generally, what the glass that people have is not quartz glass. It's the silicon dioxide. Again, this is the major component of it. This is what makes the glass. But we add this thing that's sodium carbonate, again a molecule of the sodium, carbon, and oxygen. This is sodium carbonate. We can call it baking soda or washing soda, depending on what kind of form it is. But anyway, so we add this baking soda or washing soda to it, and we'll get soda glass. That is, again, it's a form of glass. It doesn't have the drawbacks of quartz glass, but certainly doesn't have some properties that are important in chemistry. But anyway, for standard use, we add this sodium